Hi, everyone. Thank you for this opportunity. My name is Omar, and I'll be talking about the project which I'm leading, Supercomputers and Superpositions. I'm a postdoc at Durham. I'm going to be a bit cheeky and get the project team out of the way now. It's just me and my colleague, Alistair, so I don't think that deserves its own slide. Apologies for violating the template. But anyway, this is our project. And really, the goal of this project is tackling this question. How can we make quantum accelerators accessible within HPC frameworks? Now, there's a few words in there which you may or may not be familiar with. I'm not going to talk about why quantum computing matters. I think most people here have at least heard the hype or the potential for hype. Instead, I'm going to focus on the key terms here. Why am I talking about quantum accelerators embedded within HPC? Let me try and motivate this with perhaps the most famous quantum algorithm out there right now, which you may have heard that, oh, they're going to break RSA. Yes and no. Anyway, let's deal with Shor's algorithm for factoring. And let me use this as an example to make a specific point. Now, this is often touted as the milestone quantum algorithm. I want to put a lot of things in boxes and never talk about what's inside the boxes. But the point I'm trying to make is the algorithm requires a large amount of classical number theory, both on the input and the output. Essentially, the problem of factoring, the key insight, was reducing this to finding the periodicity of a function. That's over there. Finding the period of this nasty function doesn't really matter what. This insight comes from classical number theory. So if this is your problem, and all you want to do is find the period, this is where Fourier transforms can be useful. And the quantum Fourier transform is quote unquote exponentially faster than classical Fourier transform. So the power of quantum in this algorithm really is only coming in for this period finding problem, this central quantum Fourier transform. Everything on either side of it is still classical. So it wouldn't be crazy to consider this quantum algorithm really as a quantum accelerator for a specific bottleneck surrounded by classical infrastructure on both sides. So that's the viewpoint I'm going to take forwards with quantum computing. And I hope that this highlights it even with one of the most famous quantum algorithms. But yeah, once you know the periodicity, you can find the factor, but sure. We can talk about the implications of this for RSA later. But what I want to focus on now is why should we care about this idea of quantum accelerators embedded in HPC? Well, one thing I've just tried to point out is that there's a large consensus that quantum computers will never completely replace classical. Yeah. So the meaningful path to advantage, it probably leverages hybrid techniques. Or at least it will, depending on your perspective. So what you should be thinking about doing is integrating quantum processing units and classical processing units. Yeah. Next point. If you look at the published national quantum strategy right now, it already highlights that there is a key skill shortage in the field of quantum computing. The UK government knows this. In their strategy, one way they've taken to address this is increased funding for CDTs in quantum computing, etc. Sure, good strategy. I would argue that a complementary path to this is equipping domain specialists with quantum literacy to accelerate their own domain science. And I would argue that perhaps done in tandem, this is more efficient instead of raising up domain specialists from the ground up in every single field who can use quantum. And if you're trying to equip domain specialists, what better way than within HPC frameworks, which are being used by domain specialists? So that's something we should be doing, I believe. Another problem on the left is current access to quantum computers is very fragmented. It's usually group specific. Someone's got like a quantum computer in a shed, and it's very hard for other people to access it. So we should be thinking about federating quantum access to make it more accessible to the widest range of users across a diverse range of disciplines. And perhaps one of the most obvious reasons we should care is many people have heard about quantum, but they don't really know where to start, right? Many of you are experts who've spent years devoted to your field of interest. You might be interested about this. Is it just a buzzword? Can it help me? Can it not? And really the only way to know is by eliminating entry barriers to quantum computing for new users. So I've tried to motivate the problem on the left and give you some plan of action on the right. And really the right is what this project is working towards, implementing or at least laying the groundwork for this plan of action. So to get there, there's a couple of challenges we have to address. quite a few challenges actually, but for now, let's deal in broad strokes. On the left, I have some of the main technological aspects. Okay, for starters, if you're integrating quantum and HPC, you're going to have to deal with some sort of coupling paradigm. There's options out there, tight versus loose coupling, depending on how you're integrating your TPU, QPU onto the same stack, co-locating versus other forms. All of these are a bunch of technical challenges I don't really want to get into now. For the benefit of people who might not be able to read in the back, I'll just mention them briefly. Obviously, you have hardware interoperability. You have two fundamentally different types of hardware here, quantum and classical. Hosts of challenges there. Software is not just the same as coding from Python to Fortran. It's a fundamentally different coding paradigm. With it comes execution models. Even if you have your quantum processor and your classical processor, how are you leveraging the two different resources? That will obviously come with bottlenecks and latency, synchronization. You don't want one system waiting on the other. And coming with this are the bunch of auxiliary routines you'll need, scheduling, unified containers for your hybrid programming environment, et cetera, et cetera. Technological challenges, which this project hopes to address, but I don't want to focus on now, because I think the second type of challenge will be more interesting while I have you people here. And those are community challenges. Like I just mentioned, we have a limited quantum-aware talent pool. And I would like to split this into two distinct branches of the same tree. We have gaps at a researcher level where we have domain experts who may be interested, may not know much, maybe they do know much, but getting these people quantum aware. But there's also in tandem with that, there's plenty of young people out there who probably want to get into quantum at some point, but they don't even know how to start. And like I said, current access means, yeah, there's a lot to be said about making that more open. And there's also a very steep learning curve for quantum, especially if you're coming from classical domain science. So these technological and community challenges are something this project hopes to assess. But in particular, I want to spend a minute or two talking about how we're dealing with the community aspect for now. Okay, disclaimer, the project hasn't officially started yet, but this is where I envision it going. We've forced, very politely, the following partners to engage with us. For starters, ULIC Supercomputing Center in Germany are currently some of the best, arguably, at integrating heterogeneous hardware, quantum and classical. So they're experts in both the hardware side, the training side, and providing unified container access to a broad group of users. So they're happy to cooperate with us. We'll organize a research visit, and we'll liaise with them on how to, on their challenges they face, successes, et cetera, et cetera. Quartz Interactive. This is a video game provider on Steam, which I do not own, but it's interesting. They have a scientifically rigorous game which explains the principles of quantum computing almost mathematics free. I'll come back to this in a second, but just keep in mind that this exists. Okay, then we're also working with EPCC. I was talking to a few of them earlier. They already provide regular training for HPC users, so it's very natural to talk about how we can include quantum in that. The NQCC, the National Quantum Computing Center, have already agreed to provide funding for community-based workshops. Look out for that. I'll comment on that more in a second. And we're hoping to target specifically underrepresented communities. And one idea I've been playing around with is taking this video game into schools, perhaps in the Northeast, and looking at user engagement with students. Because it's tailored for non-experts, right? So if we show people that this stuff is out there, what's engagement like? Can we make it more appealing to a broader group? So these are the main people we're hoping to tackle this community challenge with. And brief outline of the structure of the project. I promised we would look at those technological challenges I blurred over. Yeah, okay, we're not going to solve those problems in the matter of a few months. The goal of the project is to assess challenges, highlight priority actions, and lay the groundwork for more targeted efforts there. At the end of the day, we only have a few months on this, but we're hoping to establish a clear evidence-based view of the main technological challenges now. Community, I've just spent some time talking about. Two-pronged approach at the research/domain specialist level, as well as underrepresented communities who may not have had the chance to access quantum. And then the work package 3 is consolidating the insight from technology and community to highlight priority interventions and so forth. So that's basically the scope of the project. bit of technology, bit of community, bring it together, make it more accessible for everybody. That's what I'd like to summarize, that yes, quantum computing has the potential, huge caveat there, to accelerate key classical bottlenecks. But really, what I'm hoping for is classical specialists to help identify these bottlenecks, working with quantum specialists, bridging those gaps so that we can actually leverage it in a meaningful way. And one of the big problems with that are these high entry barriers from a community perspective, which we're hoping to identify and work towards breaking down. We will address both technological and community, keep an eye out for community workshops. There's already going to be a quantum HPC session at Durham HPC Days, which we proposed. I would like to highlight that these workshops are a two-way discourse. It's not just going to be talks aimed at an audience and they walk away. We're really hoping for audience input in the breakout sessions, et cetera, et cetera. And yeah, if you'd like to be involved in any way, my email's down there. If you can't read it from the back, it's just my name, Omer.Rathore at Durham. Thank you.